So let's discuss some examples of many-body quantum systems. In order to understand the Hilbert space for a large collection of particles, you need to understand the Hilbert space for a single one. So let's take the simplest particle we can possibly imagine, one with no internal structure. Maybe it might be an atom where only one level is important, and therefore the entire Hilbert space is described by a single position, x, that might be in 1 dimension or 3 dimensions. So that's our set of basis states, and we'd have a Hamiltonian for a single particle, which is just the kinetic energy plus the potential energy. Now, if we wanted to consider many particles, then we might want to write this original Hamiltonian in terms of bras and kets, where now these p's and these x's are simply complex numbers because the operators are done in terms of bras and kets. And in that notation, it's very easy. We've seen how to translate to get the Hamiltonian for many particles, where these operators here create and annihilate particles with particular momentum, and these operators here, these phi's, create and annihilate particles of particular positions. And we know how to change basis. It's very easy for the creation annihilation operators, so we could turn either of those position or momentum operators into the other kind. Let's put them all into the position basis. And of course, in that form, it looks very much like the Hamiltonian in the single particle position basis. And that's not surprising because, of course, the many particle situation also contains the single particle example as a specific case. But these phi's here, these operators, remember, are annihilation and creation operators in the many-body Hilbert space. They're not the wave function. There's no sense in which they are just wave functions, even though the formalism makes them look very similar. If we'd been really clever, we wouldn't have gone into either the position or the momentum basis. Now, obviously, for this term, the position basis is the best basis because it makes everything diagonal. And for this term, the momentum basis is a really good basis because it makes everything diagonal. But you can't be simultaneously in both of those bases very easily. The basis in which everything's diagonal is, of course, the energy eigenstate basis. Now, for a single particle, that's just where these annihilation and creation operators create and annihilate particles with a particular energy. So in the particular energy eigenstate of the single particle Hamiltonian. Now in energy regimes where those are discrete, they would have a sum, and in energy regimes where they were continuous, you might have an integral there, but either way, it would still be diagonal. Now for this incredibly simple system where we only have the spatial degrees of freedom, for what kinds of states are we going to have non-trivial many-body quantum effects? In other words, what kinds of states are we going to have the fact that these things are either fermions or bosons have any real effect on their behavior? And the answer is typically when we try and have high density for these objects. So supposing these things are fermions, then whatever basis we take, and we can always go out of the position basis and into some other one, whatever basis we take, we can only ever have either 0 or 1 fermion in that state. So suppose we have some kind of potential that's going to try and put all our fermions in a small area. Maybe it's a well of some kind. Then as we try and put our fermions in this area, we can look at the states with all the different energies. And because we can only ever put 1 fermion in each state, then you can see that the more fermions we put in, we're going to get more and more energy per particle required, and we're also going to see that the volume is going to get bigger and bigger. So there's a kind of tendency for fermions to spread out, and this causes an effect called Fermi pressure. And it's actually this effect that stabilizes things like white dwarf stars or neutron stars. If you didn't have that Fermi pressure, that inability for them to actually join the same state, then those stars have enough gravitational pressure to collapse further. And so what you have there is a star acting very much like an atom. The atom can't have all the electrons go into lower energy shells, and therefore the atom stays with the structure that it has. And stars work the same way. Now, if on the other hand these particles were bosons, then not only would they be allowed to be in the same single particle quantum states as each other, but they would also exhibit a tendency to transition to those states by preference. And what that means is that as you, say, cool down a bunch of particles in some trapping potential like this, if they're bosons, there comes a particular point at which the number of particles, in particularly the lowest one, gets high enough that it starts to stimulate transitions into that state. And then you have a runaway effect where all your particles end up being in that bottom state, in the same single particle quantum state, and that's called Bose-Einstein condensation. The phenomenon of Bose-Einstein condensation would be a little unamazing if it occurred when the temperature was down here. So if the average energy of the particles was lower than the first excited state, it would be extremely unsurprising to find the bulk of them in the lowest one. But in fact, it tends to happen when that kinetic energy is in fact hundreds of excited energy levels up. At that point, we just start to get a little bit of non-zero occupation in that lower state, and then the effect of Bose enhancement, where the rich get richer, starts to take over, and transition to that ground state get larger and larger, and then at a critical point when the temperature is way up there, suddenly you get all the particles in this single state. In the original situation where it was predicted, where we in fact don't have a discrete set of energies but a continuous set of energies, so for example for free particles, it's far more dramatic again. So in that case, if for a given distribution we for example plot the momenta or total velocities, we get some kind of distribution, and we find that as we make it colder and colder, what of course happens is that this peak moves and gets tighter like that. And that will happen as you get colder and colder. Then there becomes some magical temperature, some transition temperature where you get a phase change. And instead of having just that continuous distribution, you also have a non-trivial fraction of the particles all having the same momentum zero. So in other words, we have a delta function appearing in our distribution function. And that's the example of Bose-Einstein condensation. And that happens at a finite temperature, which is non-zero. And as I said at the start of this video, all of these effects happen at roughly the same time. They happen at the time when the density of these particles becomes sufficient. The tendency for two particles to overlap and be in the same quantum state becomes non-trivial. So for fermions, that has a strong effect because they're not allowed to do that, and so they get pushed apart. And for bosons, that has a strong effect because they have a tendency to do that much faster than classical particles that are distinguishable. Strangely enough, in many-body quantum mechanics, if you have on average n particles all in the ground state, that doesn't completely specify your state. So if I were to write down the state in occupation number notation, that looks like it's pretty unique. So you've got n particles in the lowest energy state and 0 particles in all the rest. But in fact, there are other possibilities that also have the same average number of particles. Because remember, in many-body quantum mechanics, you can have superpositions of things with different numbers of particles. So in fact, you could have this instead, with some kind of condition, and that has the same number of particles on average, but it has a superposition of different numbers of particles. And you can see that those coefficients, C of n, have a lot of freedom. They can have different phases. You can have all sorts of complicated things. They could be coherent states, number states, squeeze states, and all these things we can explain later. You have states that in some representations spell out Joe is great. Exactly which one of these physical states is relevant to your physical system depends a lot on the dynamics of how you got there. For example, if you take a well-defined number of atoms and you manage to cool them down, you'll end up with a number state with a well-known number of atoms. In other words, it'll be something a little bit more like this one. In a laser, when you tend to get a large number of bosons going into a well-defined mode, you in fact tend to get a coherent state. A coherent state looks more like this, with particular choices of the coefficients there.